The new question number 1 here. Here we have 0.2 molar HCl, and all we want to know is the pH. Now again, the one thing that you need to know in order to answer this is that HCl is a strong acid. So 0.2 molar HCl is the same as 0.2 molar hydronium. We remember that once we know hydronium, we simply need to take the negative log, plug it in, and it's 0.7. Yeah.
Are these problems in here?
Yeah. Maybe. They should be, they were in the one that was online to print.
Yeah. Is that not what this is?
That's, no. So I changed the first one.
Yeah, they are different, some of them.
Yeah.
Like this one I got printed from them, and this one was from last class.
Oh yeah? Okay, I don't know. Anyway, this is it. If we have hydronium at 2.35 times 10 to the minus 3 molar, is this solution acidic or not?
It's acidic.
It is greater than 10 to the minus 7, so it is acidic. We know that if we know hydronium, we can calculate hydroxide simply by dividing 10 to the minus 14 by hydronium. We could also do it this way, convert hydronium into a pH value. If we take the pH, we know that pH plus POH must equal 14. So we simply need to subtract our pH value from 14, and we get 11.31. If we know the POH value, simply remember that 10 to the minus POH is equal, log of hydroxide is this. Here's our POH, negative log 4.26 times 10 to the minus 12 molar. This would be much, much easier, much faster if you simply did this, 10 to the 14 divided by hydronium to get hydroxide. Make sure you have both approaches written on your card. We take nitric acid, we dilute it to 1.5 liters. What's the pH? Once again, nitric acid is a strong acid, so we're starting off with 0.16 moles of hydronium. We're going to dilute this to a total volume of 1.5 liters. Hydronium is simply 0.11 molar. If we know hydronium, we simply need to take its negative log. So we type it in, hit log, change the sign. pH is 0.96. This may be the same one we had last time, but we have a pH of 3. We're diluting a solution from 2 to 4 liters. What's the pH of the new solution? Well, if our pH is 3, that means hydronium is 10 to the minus 3 molar, right? If we know hydronium is 10 to the minus 3, our initial volume here was 2 liters. Our final volume is 4 liters. This is simply equal to 5 times 10 to the minus 4 molar. Again, if we know hydronium, all we have to do is take its negative log to get pH. Now, just off the top of your head, if we had diluted this from 2 liters to 20 liters, what would our pH be? Just off the top of your head. We're diluting it tenfold, right? So if we started with 10 to the minus 3, it's going to be 10 to the minus 4 now. So that would be pH 4. Remember, change the pH by 1 unit. That's a factor of 10. All right, 0.05 molar lithium hydroxide, and we want pH. Lithium hydroxide is a strong base, so this is 0.05 molar hydroxide, correct? If we know that, we can simply take hydroxide concentration, calculate pOH. To get pH, we simply subtract 14 pOH minus, or 14 minus pOH, and that will give us our pH. Type in hydroxide ion concentration, hit log, change the sign. This is 1.3. If the pOH is 1.3, 14 minus 1.3 is 12.7. pH plus pOH is always going to be 14. Any questions? Type in hydroxide, hit log, change the sign, you get 1.3. 14 minus 1.3 gives us the pH. Now this guy is a little more difficult. You have to just think a little bit about what's going on here. We have a strong base and a strong acid. If we added the same number of moles, they would just cancel, right? We would wind up with lithium chloride in water. But this is a titration in progress, okay? After we've added 23 mils of our HCl, we need to know if we have titrated off all of the lithium hydroxide or if there's some left. The way to do that is to simply figure out how many moles you have of each, how many moles of hydroxide this represents, and how many moles of HCl this represents. Now moles is simply going to be concentration times volume. So for lithium hydroxide, we have 0.2 molar. We have 35 mils. For HCl, we have 0.25 molar, and we have 23 mils. So after we've added our 23 mils, we have added 0.58 moles of HCl to our 0.0058 to our 0.007 moles of hydroxide. That means that we still have excess hydroxide, right? Started off with 0.007 moles. We've added 0.058 and neutralized. We now have an excess of lithium hydroxide. So, the excess is 0.012 moles of base, this minus this. So we know we have excess base. We know how many moles. We could get molar concentration from the volume. The volume is going to be, do I have it here? We have to add these two volumes together. So we have 35 mils, 23 mils, that's 58 mils. Remember, we've added the two volumes together. So now we know the total volume, and we know how many moles of base we have. So we are 0.012 mole. Simply divide moles by volume. Finally, once we know our molar concentration here, we just type that in, hit log, change the sign, that gives us pOH. For this problem, pOH is 1.68. pH is 14 minus that. So 14 minus that is 12.32. Now this takes a little bit more logic than the standard problem. You might see something like this as an extra credit. Again, all you do is figure out the moles of each, to see which one is in excess. We have 0.0012 moles in excess. Total volume, 58 mils. Get our concentration, negative log, 14 minus that. So lots of steps, but really not complicated. Any questions? All right, this should look a whole lot like the tutorial to you. This is a problem straight from the tutorial, put directly on the exam. Solution has a pH of 5.29. I want hydronium, hydroxide, and pOH. pOH is the easiest, isn't it? We just take 14, subtract our pH, and that gives us pOH. Our pOH is 8.71. Hydronium. Well, we know a pH. We know that 10 to the minus pH is going to give us hydronium. So we simply type in our pH value, change the sign, and hit 10 to the x. And our last one, we're going to do it the same way. If we know a pOH value, we can get hydronium by 10 to the minus pOH. Type in 8.71, change the sign, hit 10 to the x, and that's our hydroxide ion concentration. Exactly like the tutorial, please, if you have any trouble with these, do the tutorial. I can assure you that you will get a problem like this directly off the tutorial. I'm just going to go hit the button, hit the numbers, type it in. Okay? Now we kind of talked about this already. If I have a solution, this pH 6, and I raise the pH of that to 7, what has happened to hydronium? First of all, we go from 6 to 7. Does hydronium go up or down? At 6, it's 10 to the minus 6, isn't it? At 7, it's 10 to the minus 7, so that's less. So, we're looking for the less. Did it decrease by 1 pH unit, 100, or 10? Once again, 10 to the minus 6, 10 to the minus 7. Decreases by a factor of 10. Phosphoric acid, we use that in lab. I said it's a triprotic acid, isn't it? Triprotic acid means it's going to lose all of its acidic hydrogens. First one comes off, second one comes off, and the third one. When the third one comes off, what are we left with? If we lose 1, we get dihydrogen phosphate. If we lose 2, we get hydrogen phosphate. If we lose 3, we get phosphate. Simple acid-base reaction here. Pay careful attention to the words. We're looking for the Bronsted acid and the Bronsted base for the forward reaction. What does a Bronsted acid do? Donates a proton. What does a Bronsted base do? It accepts a proton. HCl is going to be our Bronsted acid, and it's going to donate a proton to ammonia. So we're looking for HCl as the acid, ammonia as our base. All right, the reverse reaction, so we're going backwards here, and instead of Bronsted acid base, I want to know the conjugate acid base pair. So when you're doing that, you look and you say, for this reaction going back, what is going to be the Bronsted acid? Because that's where you want to start. Which one of these is the acid? And then once it loses a proton, it forms its conjugate base. So what's that? This compound functions as an acid, doesn't it? And when it loses its proton, what does it form? Ammonia. Conjugate acid and base must be the same compound, just differing by a proton. All right, which of these is not a conjugate acid-base pair? Remember that it must be the same compound, differing only by a proton and a charge. Well, this is the same compound, isn't it? This is the same compound, that's the same compound, that's the same compound. So we're not going to get it that way. We need to look and see which one we want the acid to be first and then the base. If this functions as an acid, it's going to lose a proton and a charge and get ammonia, right? If hydroxide functions as an acid, and it can, it could donate this proton and it would form O2-. If hydrogen phosphate functions as an acid, dihydrogen phosphate, it would lose this proton, gain a negative charge, and give hydrogen phosphate. If this functions as an acid, gives up the proton, another negative charge to give carbonate. However, if amide anion loses a proton, it would form the amide dianions. Therefore, this guy is not an acid-base pair. They differ by 2 protons, so that should be a dead giveaway. You're looking for something that differs only by 1. What can we say about strong acids? Do strong acids always contain halogens? No, sulfuric acid is pretty strong, right? Percentage dissociation is usually in the range of 99.999. What makes it strong? It dissociates completely, doesn't it? Strong acids can only be prepared in concentrated solution. Well, that's silly. And they're always monoprotic. Oh no, think about sulfur. So this guy here is a correct answer. Once again, think about the movie with HCl. Every HCl that was on the screen there separated, didn't it? Virtually 100% ionization. All right, if we take iron 2 hydroxide and HCl, what salt will we make? We know strong acid and a strong base give a salt, right? The salt here is going to be between iron 2 and chloride. This is silly. That's sillier. So is that. That's strange. And this is iron 2 chloride. If you took copper 2 sulfate and reacted it with copper 2 hydroxide, reacted it with HCl, you would get copper 2 chloride, wouldn't you? It's just simply exchanging the ions. If we multiply hydronium times hydroxide, what do we get? You've even got this written on your 3x5 card, don't you? Hydronium in neutral solution is 10 to the minus 7. Hydroxide is also 10 to the minus 7. Multiply them together and you get 14. I like this kind of problem. It kind of tests just your sense of acids and bases. Which of these is not basic? Now, in order for something to be basic,
Yes.
hydronium must be less than what? Must be less than 10 to the minus 7. If hydronium is less than that, then it's a basic solution. So this is 10 to the minus 13, 10 to the minus 8, 10 to the minus 9, 10 to the minus 11. Those are all less than 7, aren't they? This guy, however, 10 to the minus 3, this is more than 7. So this solution is acidic. If hydronium is 10 to the minus 9, what would hydroxide be? You can tell right away that this is a real test question, can't you? Because you can do the math here in your head. 10 to the minus 14 divided by 10 to the minus 9 is what? 10 to the minus 14 divided by 10 to the minus 9 is 10 to the minus 5. All right, which of these does not describe an acidic solution? If the pH is less than 7, is something acidic? Yes, absolutely. If hydroxide is 10 to the minus 11, well, if hydroxide is 10 to the minus 11, hydronium must be 10 to the minus 3, right? And that makes it acidic. If hydroxide is greater than hydronium, the more base we have, the more basic it is, correct? Let's just finish these. If hydroxide is 10 to the minus 10, hydronium must be about 10 to the minus 4, right? And finally, if we add 1 mole of acid to 0.1 mole of hydroxide, what are we left with? 0.9 moles of acid, right? Which is acidic. These are very nice concept questions. Make sure you get these, because this is the kind of thing that's going to show up. Questions based on the tutorials and concept questions. We'd be left with 0.9 moles, and that makes it acidic. If our pH is 3.26, what is hydronium? Again, exactly off the tutorial. To get hydronium, we remember 10 to the minus pH. Type in pH, change the sign, hit 10 to the x, we get 5.5 times 10 to the minus 4. If our pH is minus 0.26, remember pH can be negative and it can be above 14. What's our hydronium? Same exact problem, isn't it? All we want to do is, remember, 10 to the minus pH. So we type in our pH, which is minus 0.26, change the sign, and hit 10 to the x. Once again, which of these is not a conjugate acid-base pair? We saw a question very similar to this, and I gave that on the review. And then on the exam, I gave this one. Must be the same compound. Okay. They must differ by 1 hydrogen and a charge. Lose 1 hydrogen, lose 1 hydrogen, lose 1 hydrogen, lose 2 hydrogens, lose 1 hydrogen. Clearly, 2 is not 1. Lose 1 hydrogen and the positive charge associated with it. Usually that ends up in giving you more negatives. Simple titration here, isn't it? 20 mils, 0.4 molar base. We want to know what volume of 0.5 molar sulfuric acid we need to react with it. 2 things we have to remember. Well, first of all, always concentration times volume is moles, so that's fine. But sulfuric acid is diprotic. So it takes half as many moles to react with 1 mole of base. Step 1, how many moles of base do we have? That's concentration times volume. We have 8 times 10 to the minus 3 moles of base. Now, 2 moles of base react with every sulfuric acid, don't they? So, we only have half as many moles of sulfuric acid as we do this. 8 times 10 to the minus 3 moles of base, 4 times 10 to the minus 3 moles of acid. Again, because every acid gives 2 hydroniums. All right, so we know a concentration here. We know the number of moles. We just calculated it. And all we do is solve for, oops, that should be our volume. Change that to volume, please. And this is 8 milliliters. Now this one is just like the one we did earlier. Once again, on the sample exam, I gave the other one. We went over it in class, and then on the real exam, I gave this one. Slightly different format, but I gave this one. What we need to do is see how many moles of base we have, how many moles of acid we have, see which one is more. Do we have more acid or more base? take whichever one is in excess, subtract the 2, take the excess, add your volumes, divide to get a concentration. Base, we have 0.006 moles. Acid, we have 0.006 moles. We have slightly more base than we do acid. Okay? Slightly more moles of base than we do acid. We have an excess of 4.5 times 10 to the minus 5 moles. We're going to add our 2 volumes, because remember we added the 2 volumes together. So our final volume here is 20 mils and 40.3 mils, or 0.0603 liters. Moles divided by liters gives us molarity. Now that's our moles of base, right? Simplest way to do here is to convert molarity into pOH. How do we do that? Type in 7 times 7.46 times 10 to the minus 4. Hit log. Change the sign. We should get 3.13. 14 minus 3 is 10.87. Again, it's a complicated problem. But it's a nice extra credit sort of thing because it does test your concepts for everything. Which of these has a pH of 10? If our pH is 10, what's the hydronium ion concentration? 10 to the minus 10 molar, right? Do we see that anywhere? No. This is 0.1 molar acid. That's strong acid, isn't it? So is that. Same thing. So is that. Here we have 2 hydroxide solutions. If our hydronium is 10 to the minus 10, what's hydroxide? 10 to the minus 4. Exactly. Hydroxide must be 10 to the minus 4, and this is the answer. And our last one here, out of the pH set. Lactic acid. When you exercise, your body burns glucose. Lactate or lactic acid can accumulate in your muscles, metabolized in your liver, etc., etc. That's why your muscles hurt and you get a pain in your liver, etc. All right, lactic acid has, well, I can't give that away, can I? This is the conjugate base of lactic acid, C3H5O3 minus 1. Okay? That's the conjugate base. Which one of these is lactic acid? To form the base, we're going to do what? We're going to lose a proton, right? And we're going to lose the positive charge that goes with it. So if we start with the base, all we do is put the proton back with this positive charge. So we take this guy, add a proton, add a charge, We need C3H6O3. We've added one positive charge, so it must be neutral. This is what lactic acid looks like. This is the conjugate base. This is the acidic OH here. And all we're doing is losing this proton and its positive charge to form this. All right. Our third hour exam review. Let's take a quick 5-minute break. If you don't have a copy of these questions, again, I've got a copy up here. Like I say, we'll do this in 5 minutes. Remember, it's a very nice way, very nice, concise version of the main points in the chapter. So a nice way to review. We're making aluminum bromide. Aluminum bromide actually exists as a dimer, Al2Br6, which is not the lowest whole number ratio, but it does describe what the molecule looks like. So that's why it's okay to do this. We are going to make 2.43 moles of aluminum bromide. How much aluminum do we need?
So the given is 2.3
Simple
Okay.
stoichiometry. 2 moles of aluminum gives 1 mole of aluminum bromide. So how many moles of aluminum do we need to get 2.4?
4, 8,
Twice as much. I won't change mine. 4.86, again, 2 moles for every mole of this. If we're making 2.43, we simply need to double that. We're making ammonia. This is actually a very important process industrially because ammonia is used for fertilizers, for bombs too, but mostly for fertilizers. Very, very important. Take nitrogen and hydrogen and we can make this. It's not an easy reaction. But how many grams of nitrogen do we need to give us 328 grams of ammonia? Stoichiometry here is 1 to 2, right? How many moles of ammonia does this represent? Once we know how many moles of ammonia that is, it's going to take half as many moles of nitrogen. 1 mole of nitrogen gives us 2 of these. So, 325 divided by 17, we have 19 moles of ammonia. Half of that is 9.54. So we need 9.5 moles of nitrogen. Every mole of nitrogen weighs 28 grams, doesn't it? If we have 9 of them, we're at 267 grams. Aluminum reacts with chlorine to give aluminum chloride. We want to know a mass of chlorine that we need to react with 163 grams of aluminum. Now, step one, our stoichiometry here is 2 to 3, right? 163 grams of aluminum at roughly 27 grams per mole. We can figure out how many moles this is. The mole ratio to give us chlorine, 2 moles to 3 moles. So step one, let's calculate the number of moles of aluminum. 163 divided by about 27. It takes 3 moles of chlorine for every 2 moles of aluminum. So to get moles of chlorine, I'm simply going to multiply by 3 and divide by 2. .91 is the molar mass of aluminum trichloride. So we put all this together, and we get 643 grams. Jesus. When I imported these into this slide set, it looks like all the correct answers. The tabs were off, so it's easy to guess. You won't see that on the exam, though, I'll make sure. Percent yield here. PCl3, chlorine, PCl5. We have 119 grams of PCl5. We're reacting 61.3 grams of chlorine. PCl3 is in excess, so that's good. So we don't have to worry about PCl3. What we have to do is figure out our theoretical yield. Okay? Going to calculate moles of PCl5. We have 119 grams of PCl5 are formed. So let's calculate moles of PCl5. We have 61 grams of chlorine. Here's our molar mass, so we know moles of chlorine. We have 0.573 moles of PCl5. That's from up here. This divided by that. We have 0.864 moles of chlorine. That's this divided by that. The ratio here is 0.66. Convert our mole ratio here into a percentage, and it's 66%. Here we're dissolving 1.5 moles of lithium hydroxide in 750 mils. Oh my gosh, I hope there's a lot of these, right? We know moles. We know volume. We can calculate molarity. Divide moles by our volume. Remember, the volume must be in liters. And gee, not surprisingly, it's 1.99. If we have 1.8 liters of 1.4 molar sodium hydroxide, how many moles is that? Well, we can do that because we know concentration times volume gives us what? Moles. Simply multiply our concentration times the volume, and we get 2.54 moles. All right, we're doing a dilution here. Remember, concentration times volume gives us moles, and in a dilution, the number of moles doesn't change. So, we have a volume, and we have a concentration. That's our initial. We have a concentration, but we don't know our final volume. All you do is set up the simple concentration times volume. These two equals concentration times volume. Solve the volume, and we get 86 mils. In a dilution, the number of moles does not change. So it's simply CV, CV. If we want to make a liter of 2 moles, 2 molar urea, what would we do? Well, we're going to need 2 moles of urea, aren't we? It's 60 grams per mole, so that's 120 grams. We have 120 grams in all these. This one is stupid, but okay. When we make a solution, remember the little magic slide with the empty volumetric? What happened first? You put the stuff in, right? Then you dilute it to the volume. So we want to put 120 mils of urea, 120 grams of urea in our thing. Add just enough to dissolve it and dilute it up to 1 liter. Remember the magic slide. You put the stuff in first, then add the water. In 140, you will learn how to make a 1 molal solution. With that, you do it the opposite. You take 1 kilogram of water, then add the urea. But that's 140. We have 0.001 mole of calcium hydroxide. Takes 25 mils of HCl to neutralize it. What's the concentration of our acid? One thing you have to remember, We have 2 hydroxides here, don't we? So how many moles of base do we have? 0.002 moles of base. We're going to take the number of moles of our base, divide it by our volume of our acid. Moles divided by volume is concentration. Remember, we have to multiply the number of moles here by 2 because there are 2 hydroxides. So this is 002 moles of base. And you see, it could have been either of these. Remember we took carbonate and we added acid and it fizzed, right? We did that in lab. 2 moles of hydronium react with carbonate, 1 mole, to give water, and 1 mole of CO2. If we have 0.3 moles of hydronium, how many moles of CO2 will we get? Well, for every 2 moles of hydronium, you get 1 mole of this, right? So if we have 0.3 hydroniums, how much can we get here? We're going to get half of that. Takes 2 to give 1, so we're going to take half of this. HCl and water to give hydronium and chloride. What's the role of water?
Water is young.
What is the Bronsted acid here? HCl is the acid. What's accepting the proton? The Bronsted base is, right? So water here is functioning as a Bronsted base. In this reaction, what's nitrate doing? Nitric acid doing? Well, what's it doing? What's happening here? This is donating a proton to water. What donates a proton? An acid. It's a Bronsted acid. Once again, I told you I like these questions. Which of these is not basic? In order to be basic, hydronium must be less than what? If hydronium is less than 10 to the minus 7, it is basic. So you simply look at these and say, which of these is greater than 10 to the minus 7? Same question we had before, 10 to the minus 3. If hydronium is 10 to the minus 9, what's hydroxide? You In your head, you can do this. 10 to the minus 14 divided by hydronium gives hydroxide, and that's 10 to the minus 5. Which of these does not describe an acidic solution? If the pH is less than 7, is it acidic? Absolutely. If hydroxide was 10 to the minus 11, what would hydronium be? 10 to the minus 3. That's acidic. If hydroxide is greater than hydronium, nope, that is not acidic, because you would have more hydroxide than hydronium. It would be basic. Again, if hydroxide is 10 to the minus 10, hydronium would be 10 to the minus 4. And this one again, 1 mole is added to 0.1 mole of base. We will have excess hydronium, and it will be acidic. If the pH is 3.26, what's hydronium? Look at your magic card, 10 to the minus pH, right? Type in pH, change the sign, hit 10 to the X. 5.5 times 10 to the minus 4. And then the last question here. Remember, your exam will be 20 questions with an extra credit. If, actually we saw this, if the pH is minus 0.26, what's the hydronium? Same problem as before. 10 to the minus pH. Type in 0.26. Hit 10 to the X. And we have 1.8 mole. All right, we will do the carbonate lab on Wednesday. Wednesday night, around midnight or so. Quiz 3 goes off, quiz 4 goes on, and the sample exam will be posted.